Okay, thanks for coming to today's CITP Lunchtime Seminar. We're fortunate to have Muneeb Ali, who's a final year PhD candidate here at Princeton. He's been working a lot on blockchains and has actually has a startup called OneName. So he's done some very interesting work recently using blockchains to develop decentralized mechanisms for both DNS resolution and for building a decentralized PKI. So Muneeb's going to tell us about his work today. So thanks a lot, Muneeb.
All right, awesome. Yes, so as Nick mentioned, that I'm a co-founder of OneName with Ryan Shea, and actually Jude is sitting here as well, and a lot of his work and Ryan's work went into this. But Blockstack is the open source project, and that's kind of like what I'm representing today. So this project is like too big for being any one person's work. So I actually have a slide later on where I'll tell you about everyone who's involved with it. So today I'm basically going to go over like what's the problem we are solving. I wouldn't assume that people know about blockchains, so I will quickly give you the very basics that you need to know. So our first production system was actually on a different blockchain, not the one that most people know about, that is the Bitcoin's blockchain. It was a system called Namecoin. So I will present like what are the lessons that we learned from our year-and-a-half long production system, and then why we migrated over to the Bitcoin blockchain and built a new system called Blockstack. Right? And I'll go over some of the interesting work that's going on right now and where are some of the opportunities where maybe you guys can get interested in and try to like collaborate or something. So at a very high level today in the internet, like this is kind of like how things roughly work, right? Like if you want to go to some website, let's say Facebook, the first thing is like, hey, how do I talk to Facebook.com? What is the actual IP address and the server that I need to talk to? And the second is that, is this the correct Facebook.com, right? So these are two separate problems dealt with two different services in the internet infrastructure. The first is DNS. Most people are familiar with it, the domain name system. It gives you a resolution between a human-readable name like Facebook.com to the actual IP address and the destination that you should be talking to, right? And the second system is public key infrastructure or certificate authorities, which will basically tell you that you are talking to the correct entity. Right? So that's usually most people would see in their browser the HTTPS sign and with a lock, and with a lock they're like, okay, I'm secure, I'm talking to the right party, and that's how the world works. There's another layer that once I know that I'm on Facebook, how do I tell Facebook who I am, right? Or this could be any other site. It could be GitHub, it could be Medium. So usually these service providers would have some sort of an authentication layer. Right, so Facebook will give you a username and a password. So the picture that emerges is something like this. A user wants to talk to a service. The service has all of your data. So Facebook has all your pictures, all your messages, everything. And they will implement, like in their data centers as a service, some sort of an authentication layer. Right? If you can pass through this authentication layer, they will give you access to your data. But they're holding on to it. And that's how the world works. Like that's how LinkedIn works. That's how even GitHub works. So the code that you're writing is on a centralized data center, and then you have to authenticate to GitHub to get access to it, right? And before that, two things happen. One is DNS resolution, and the other is the PKI system that we just talked about. And there's no real technical reason why these two need to be separate. It pretty much happened for historical reasons. Like DNS started with like literally etc/host.txt records. It was a file. People had the mappings in there. You can clearly see it wasn't scalable. After a while, people started building out DNS root servers. Then they tried scaling it out. And now you have all these DNS caches everywhere, and so on and so forth. But if you squint your eyes and just like look at the bigger picture, what's happening is that there is this entity. You can think of it as a federation called ICANN that kind of like controls DNS, right? So it's not entirely true that it's a centralized system because it's a federation, and different DNS root servers are actually owned by separate organizations. So it's actually pretty hard to take down if someone actually launches an attack against DNS. And then for PKI, you have companies. Like VeriSign is the most famous one, and that's how kind of like the world works. So we have made our peace with DNS being like semi-centralized, PKI kind of like depending on a few large companies, and then complete centralization of services, right? It's like we're dependent on the Googles and the Facebooks of the world. And this is kind of like the internet today. Now, what are the problems? The first one is this idea of a golden key access, right? So this was a very interesting story where a hacker was able to dial into AT&T and within 2 minutes gained access to someone else's account, changed the password, got that person locked out of his own account, and added herself as a user. Right? So it's almost like a complete takeover of identity or an account because AT&T or the customer support representative that was there holds this golden key and they can decide who gets to access this account. And this comes up in different contexts, right? Like when FBI is going against Apple, they're fighting over having access to a golden key, right? Like, do I have the authority to access your data at any time or change things, right? The second problem is that once there is centralization of data, it also becomes a central point of failure. So GitHub was actually under attack, apparently through China, and GitHub went down. Like if you're a software developer and all of your code is on GitHub, and suddenly you can't do work anymore because a company is under a DDoS attack, I think that's a problem that we need to fundamentally rethink. Why are we designing our systems in a way that an attack on a single company can actually stop like thousands of people from working? Oh, millions probably, yes, absolutely. And the third thing is this general category that once you put all the data in a single place, it will get hacked. This news story, the data was actually medical records, and the hackers were demanding $17,000, ironically in Bitcoin, that unless you pay us this money, we are not going to release the data. And in this particular case, literally people's lives were on the line, right? So they had to pay this to get out of it. But the problem is that this model or this idea of having centralized data, it is fundamentally broken. If it's there, someone will hack it, right? Versus the other model, and this is the pipe dream that a lot of people have, is that if you want to access a particular user's data, you will have to go and hack that user, not a company. Not like in one shot, you get access to millions and millions of records, right? And if we are to get there someday, we will need some form of a decentralized authentication mechanism. We will need some way of naming things online, like the DNS service. We will need some way of verifying that am I talking to the right party in a decentralized way. Because as soon as you cannot have a fully decentralized system with any single point of trust or failure. Like you can build the other components and then be like, you know what, all of that is fine, but let's make everyone go through Google because we trust Google, right? That single choke point then basically washes away everything else that you have done in your design, right? So that's kind of like our dream. That's like our goal. And in this talk, I'm not going to talk that much about decentralized authentication, but I'm going to focus on decentralized DNS and decentralized PKI, right? So that's going to be the focus of the talk moving forward. Any questions so far? Cool. So what are the problems with DNS? The first is internet censorship, right? The governments do try to censor the internet, and DNS is a very attractive way of doing it. If I'm sitting in China and I'm trying to go to a website and I'm not getting any results because the government is actually working with your DNS provider to ban it, right? So at that point, it becomes about a fight for having a free, open internet, right? And with DNS not being completely decentralized, it becomes a choke point for that. And I think Nick has actually done a lot of work in internet censorship. So you guys would have some background there. This, I think we have kind of like already covered, becomes a central point of failure. In this particular example, the Turkish government accidentally spoofed Google's certificates, right? So if you were in Turkey at that time and you thought you were talking to Google because a nice lock and a green sign was showing, you weren't talking to Google in that instance, right? So a single party was able to influence how the internet infrastructure was working in that instance. And the last thing, and it might not seem very important, but it actually is on a practical day-to-day basis, is just the ease of deployment and use. And I love this project, Let's Encrypt, from a couple of people who were at CITP earlier, actually. And they are trying to give free certificates to everyone, right? And the reason that a project like Let's Encrypt exists is because we have a huge problem of the ease of use and deployment of these security certificates. Right? Because there are a couple of companies, they have a couple of $1 billion worth of market cap, and they are making a lot of money just by handing out certificates to people because they need them in the current design. So it'll be really good to have a way to make this a default option, that anyone who connects to this new internet already has a key pair and a certificate attached. So these directly translate into goals for the system that we are trying to build. Right, so first, it should be extremely, extremely hard to censor. Right, I'll go into more details about it. The second is there should not be any central points of failure or trust. Like, absolutely, like we would not back off from this requirement at all. And the last is what I talked about, that why not make it secure by default? Like, why wouldn't we just give everyone a cryptographic key pair with which they can actually own their names and also give them a certificate for free, right? So obviously, as Nick mentioned, that our system, our solution makes use of blockchains heavily. And I think before we actually get into the design of what we have done, I will quickly go over like just the blockchain 101, the very basics that you guys need to know. And just a quick check, like how many people are really familiar with Bitcoin and blockchains? I know Arvind and his group are. OK, good. So I guess we need the background. So so there are many different ways of explaining how a blockchain works. I'm going to take the approach of blockchain as almost like a data structure, right? So this is a blockchain. It's divided in different blocks, right? And usually the atomic unit is a transaction. So if you imagine on the internet, the atomic unit is a packet, right? And you have packets and you basically communicate them over the network. In a blockchain, the atomic unit is a transaction, and multiple transactions go into a single block, right? So these are different blocks. And it's actually very simple because it's just a file, right? It's literally just a file on your computer. And that file is append-only, and you can think of it as an append-only global log because everyone on the network has the exact same consistent copy of that data, right? So I'm oversimplifying a little bit. So imagine that there's a network of 100 nodes. All of them start off, let's say, at point 0. Like this is the beginning of time, right? And at any given point, I'll actually explain it like this. So let's say this is the network, and you're starting from here. What this network does, and this network could be a node of Bitcoin nodes that are talking to each other in a peer-to-peer fashion. What they try to do is that there's a leader election mechanism. At any round, people who have a distributed systems background, like this is fairly standard, like you would have some mechanism of electing a leader, right? And then the leader gets to write the new block. And everyone on the network needs to basically agree that what you have written is correct. And how Bitcoin solves this problem is that these nodes are actually solving cryptographic puzzles, which are hard to compute, but easy to verify. So whoever solves the puzzle at any given round gets to write the block, and then everyone else can verify that, yes, that was the winner, this node was the winner, and this node now can write the block, right? So what this does in practice is that blockchain is you can think of it as a medium where writes are extremely slow. So a block typically comes in Bitcoin after every 10 minutes, right? It could actually take even more. But writes are fast, but reads are fast, right? Like once you have written some data, it's extremely durable. For someone to actually go back in history and change the data in the blockchain, they would need an enormous amount of computing power because they would actually have to go back a certain, let's say, height in the blockchain and recompute every single block and then produce another copy of the blockchain that has more proof of work than the current Bitcoin blockchain. And that's actually pretty hard to do with the amount of computing power that is already dedicated to Bitcoin today. So another thing that happens is that initially things are, you can think of like the last 6 blocks as something which are not exactly confirmed. So reorgs can happen here, right? But if you squint your eyes a little bit, because it's possible that some other party comes up with a longer blockchain and the longer chain always wins. So if you squint your eyes a little bit and just completely ignore the last 6 blocks, right? You're like, I don't care in which order they appear. I'm only going to look at the blockchain once there are at least 6 confirmations on any block. So you basically drop the most recent blocks. Then the blockchain basically becomes an extremely durable storage mechanism that gives you total ordering on all the operations performed, which is an extremely strong property, right? There is no central party, and you get total ordering on all operations performed on the chain. Once you have that, you can actually start building other distributed systems on top of it. And in particular, I'm going to talk about building a DNS-like naming system. So what you can do is, let's say at block 2, let's say I'm trying to register my name Muneeb, right? So at block 2, I would actually announce the hash of my name, right? Wait blocks, let's say I wait 6 blocks so the data is durable, it has been written in the blockchain. And then I'll do another operation saying that, hey, I want to register the name Muneeb, and that hash was actually the name Muneeb. The reason why I'm doing that is that you don't want someone to front run you. Let's say I was trying to register something, Jude heard my transaction, it still has 0 confirmations, and he's like, you know what, I like the name Muneeb as well, I'm going to register it. Right? So that's the step where we actually first announce the hash is to basically stop front running. Right? So nobody knows what the hash is, so they just see a hash, and then that hash is written, it has enough confirmations, and then you kind of like reveal that, okay, oh, that hash was actually the name Muneeb, which was not registered before, and now I can register it. And because this concept of time is kind of like already built in to the blockchain, we know, let's say now Jude was trying to register Muneeb as well, it's very easy to decide who gets the name, right? Whoever was able to write to blockchain first, right? And that's kind of like how our world works as well. Like if you go on Twitter and you're trying to register a new username, Twitter gets to decide that is this name registered or not. And they usually decide by who came and got the name first, right? But you are now dependent on the central party, Twitter, for making that decision. But in this system, you are not, right? It's a completely decentralized system. Similarly, once your name is registered, you can issue name updates on it. So at this time, you can think of this as a name-value pair. So you registered Muneeb, and then you can associate certain data with it, right? And in a DNS system, that data is your DNS record, right? And you can update it whenever you want to. So that's kind of like the very basics of blockchains you need to know. I'm happy to take questions about Bitcoin or blockchains in particular offline, but I'm going to kind of like leave it there and then describe our system. So how many people know about Namecoin? Surprisingly, a lot more than I thought. So Namecoin was the first fork of Bitcoin. I think it came out around 2011. And you can think of Namecoin as, at that time, and actually till very recently, people thought that to build different applications using blockchains, you would basically fork a blockchain, start a new network, change the blockchain in a way that make the necessary changes for your application, and take it from there, right? But now, I think people are beginning to realize that, wait a minute, this is almost like saying I want to make the application Pandora, and I will fork the internet, start my own network, make the changes, and then do that, right? So it seems very clear in hindsight, but it wasn't in the early days of cryptocurrencies. So that's what Namecoin did. They forked Bitcoin. They made the necessary changes. There was a good technical reason for it because they were actually modifying some things which were consensus breaking, which meant that the Bitcoin blockchain was not going to accept their changes. If they were, it would result in a hard fork in Bitcoin because you cannot introduce new functionality without changing the main consensus code. So when we were launching, like this is like now back in late 2013, early 2014, and we were like really excited about building this like decentralized, almost like a decentralized About Me or Twitter. And we discovered Namecoin, and we were debating, hey, should we fork Bitcoin again, start our own thing, or should we just like try to build on Namecoin? Namecoin was like it was being developed, but not very actively, and there were some recent security issues they had. So it was a trade-off. We ended up deciding to build on top of Namecoin, mostly because that was the fastest route to deployment. We just wanted our system to go live as soon as possible. So what we ended up doing was, Namecoin has different namespaces. So we picked a new namespace in Namecoin. You think of namespaces as like TLDs. Just like there is .com, .org, .net, a namespace like a TLD. So we started a new TLD on Namecoin and basically made this web app that allowed people to quickly register like their own username and then make a profile and actually embed all the data in the blockchain as well. Right? So this is that system that launched in March of 2014. This is Werner Vogel's, CTO of Amazon. That's his profile. And he was able to get the username Werner. I'm pretty sure he's very happy about that. And so suddenly now you have this like first username system where you're not dependent on any company. Anyone who was registering through our web interface actually had access to their own private keys. And we as a company couldn't do anything to their data. So how this works in the background is, remember the three-step, like first you register a hash. So in Namecoin, the operation was called name new, and you announce a hash. Then you do a name register where you basically show that, hey, I'm the same person because I'm signing from the same private key who announced the hash before, and now this name is registered. So the Namecoin software would basically process the blockchain and then kind of like make their own internal database saying that, okay, this is the name registered and this is the profile, and then you can go and update the data associated with it. And this image that you saw is basically just a JSON data over here. Right? So we are just like visually displaying it. And one thing that we did for the PKI functionality was that anyone can go and get the username Werner on this system. So how do we know it's the right person? That's the PKI functionality, where is it, hey, am I talking to the correct party, or is this the right person? For that, what we ended up doing was we would let people post public proofs and then link those public proofs to the profile that they just created on this decentralized system. So over here, Werner is saying, hey, I'm the same person who owns Werner on Twitter. I'm the same person who owns this Facebook. I'm the same person who owns this GitHub. So we also rolled out proofs for domain names. So now like we think of this as like probabilistic identity, that the more proofs you actually attach with your profile, the more the other person can be sure that, yeah, this is the person that I actually want to talk to. But this is like not the focus of this talk. Like we have actually made several improvements to how we handle probabilistic identity. But that is just one namespace on our new system. So in a new system, it's the .id namespace, right? And I'll talk about it in a little while. So lessons from Namecoin. Well, as I said, we picked the u/namespace. It was live between March 2014 and August 2015. We actually migrated over to Bitcoin in August of 2015. So this was, I think, one of the largest production systems running on Namecoin. We had around 33,000 total users who actually registered unique names in the namespace. And we as a company sent like over 200,000 transactions on the network to actually enable all the profile registrations and updates. And I think Arvind and his group did an interesting analysis of Namecoin, where they actually found that most other namespaces were basically had spam registrations. Because this is another problem with the Namecoin, that the actual price of registering a single name dropped so much that they actually saw a lot of spammers coming in and just like grabbing a bunch of names. And that was partly a reason why we migrated as well. And it's a fundamental problem with decentralized systems. I'll talk about this more in a little bit. So the biggest reason why we actually migrated was not because of spamming. This is, I think, December of 2014, and we started noticing that a single miner had more than 50% hash power on Namecoin. So let me explain like what that means. A blockchain or a blockchain like Bitcoin is decentralized as long as you don't have a single party that has more computing power than everyone else. Because if you do, then that party starts kind of like controlling the blockchain, and they can launch several attacks. I mean, what they can do with the blockchain is still limited, but this is still the most critical attack you can launch on a blockchain. So I wouldn't go into details. Just try to keep this number in mind, that 51% is extremely bad, and that was happening on Namecoin, right? So we first detected this in December, and imagine our situation that between March and December, we actually went through Y Combinator, we raised a round of funding, and now we have investors and users, and suddenly we discovered that the underlying blockchain that we are based on is actually no longer really secure, right? So that was kind of like, okay, what do we do about this? And we couldn't publicly talk about it until at least we had a viable solution. So at that time, we started working on an alternate implementation, and we were pretty clear that the Bitcoin's blockchain is the most secure because it has not the most amount of computing power today, but also the amount of financial infrastructure that is linked to Bitcoin is far greater, right? So Bitcoin's market cap is, I think, $4 or $5 billion right now. So if the blockchain breaks down, all of that money also disappears, right? So people have an incentive to make sure that mining centralization doesn't happen in Bitcoin. That's when we started working on Blockstack, our implementation, and by the time we went live, late August, the situation on Namecoin actually got worse. So this is a mining distribution where you can see a single miner. So it's a Chinese miner known as F2 Pool or Discuss Fish, actually had more than 60%, sometimes even touching 70% of the mining power in a given week, right? And I've actually seen weeks where it was more than 75%. At that level of centralization, it's not a decentralized system, period, right? Like it's basically one miner that is mining most of the blocks, and then there are some other small nodes who are basically fighting over the rest of the blocks. The interesting thing was that the Namecoin community, by this time, actually knew about this. And this miner was a big donor to Namecoin as well. So it's like Namecoin deserves a lot of credit for being the first system who designed a decentralized DNS system using blockchains. And it's also the first alternate blockchain that is still live today, right? Like most of these things disappear. Like someone will try to start a new project. There are like hundreds of these alternate blockchains out there, but Namecoin is still alive. Like people still use it. They're still doing active development. So they deserve a lot of credit for being the first party to do this. But it was slightly surprising to think that they were okay with that level of centralization, because that miner also owned a lot of Namecoin and was also a donor to the project. So it's like, why would they hurt themselves? Like, no, they can do whatever they want. It's not a decentralized system. So other issues that we notice on the blockchain. So this is like I told you that the average, yeah.
Questions on the previous slide. So how much compute power do they need to do that? I mean, I guess I don't understand the scale of is it If
That's
a state actor chose to attack Bitcoin,
Yes.
would it be subject to the same kind of problem?
Yes. So there are different levels of that question. I'm going to first give you the very high level that in Bitcoin, you have reached a place where you need specialized ASIC chips to do mining. Like your general purpose computers or data center servers like basically can compete. So one stat that kind of like surprises people is that if Google would take all of their data centers, and it's not a fair comparison because you're comparing servers with ASIC chips, but if Google takes all of their data centers and points them to Bitcoin, they would have like 1.5% of the network. That's all of Google, right? So it's a lot of hash power. On the other hand, a company like Intel, who is in the business of manufacturing chips, could actually just quietly work on a large amount of ASICs and suddenly appear online and take over Bitcoin if they want to, right? It will cost them, I don't know, $200, $300 million or something like that.
So it's feasible then.
Yes.
Okay. So then a state actor could.
State
hire
actor
them
can.
to do that.
A state actor can.
Yeah. Okay. And then, but then back to Namecoin, because you said it's an important alternative.
Mm-hmm.
So what did it take for presumably not a state actor to take it over? How much compute did that take?
So now think of this way, that when people start a different blockchain, they have an option to either change the hashing algorithm that Bitcoin is using, so that if someone actually wants to participate in that new network, they would have to dedicate resources specifically to that network. But again, in terms of like raw expense that someone would have to make, it's usually not a lot for a small currency, right? Because you can just drop the money, run the software for that particular blockchain, and like take over the network. What Namecoin ended up doing is they initially started off as a separate blockchain, but they quickly realized that, hey, it's easy for someone to attack the network. They started using this technique called merged mining, where they will accept they will kind of like link their blockchain with the Bitcoin blockchain, and a miner has the option, like they're only calculating hashes for the Bitcoin blockchain, but they can also quickly check the hash against Namecoin to basically get free money if they want to, right? So at that point, like the incentive is that you will get at least a subset of the Bitcoin miners to come and participate on the Namecoin blockchain as well, and they were able to. At some point, they would have like 70 or 80% of the Bitcoin miners also participating on the Namecoin blockchain, but it seems like over time some of those miners like dropped out, and there was like one large miner that had like close to 30% of Bitcoin, but then had more than 60% on Namecoin.
You mentioned earlier via China's firewall.
Mm-hmm.
Wasn't that attack a situation where the attack was on the scale of potentially millions of computers, and a more invasive form of that attack, wouldn't it have an even possibly more permanent and damaging effect on a blockchain?
Okay, so it's basically, as far as I remember, I think they were using some of their nodes that they use for deep packet inspection. So it's or like some of them are botnets, right? So it's like infected computers. All of them are trying to do a DDoS attack on GitHub. On this network, it doesn't matter how many nodes you have. What matters is how much computing power you have, right? So the type of nodes that you would, as I said, that even if you were able to somehow create a botnet out of all of Google's servers in all of their data centers, you would have like 1.5% of the network in terms of computing power.
They were using most of the people who were going around using VPNs in China were being redirected by Baidu ads to attack. So I mean, it doesn't seem inconceivable that those numbers could reach in the millions of computers in the
They could, but in terms of computing power, I think it's a different scale, right? So that's one thing. I think there is no production data available on blockchains, and I think our experience of this like 1.5 year long production deployment is like one of the first data sets that now actually people can go and look at these problems and try to correlate them with what was going on the network and try to have better visibility into these new types of networks, right? So some of the other things that we noticed was, remember I said that it usually takes like 10 minutes for a new block to come, but it's a variable, right? It goes up to 40 minutes. Sometimes it's much quicker than that, and that's fine because they're trying to target to stay in this range, right? And most of the time, Namecoin was in this range, right? But we also noticed that sometimes the delay between a block would go up to like more than 200 minutes or close to 250 minutes. And we were like, what's going on? Like we have users who are either trying to like update their profile or new users who are trying to register, and suddenly the latency is in the order of days. And then we tried plotting this data, and we saw this like weird spike in the middle. And after looking more at the data, it turns out that this was actually because of a software bug in the code where the bug was triggered when someone was trying to send a lot of transactions, which were very, very small, and miners kept crashing. And then they would like try to come back online and crash again, and they weren't able to process blocks. And the interesting thing is that we were probably the first people who noticed, because not a lot of people were using this blockchain. That was another data point that imagine if the internet goes down or something is wrong, people start yelling, right? There are a lot of people who need that system for different reasons. So you would actually detect problems much faster. A lot more people would be trying to fix them as well. Whereas if it's a smaller ecosystem and problems go unnoticed or there aren't a lot of parties involved, that turns out to be a problem. Another interesting thing, this was kind of related, is when a miner, for some reason, stopped accepting our transactions, right? And that was strange. So we were actually trying to, our target transactions were around here. We were trying to send around 150 transactions per block. And we would, basically what would happen is, you'll see a block, the miner is not accepting our transactions. Next block, they're not. Next block, they're not. And then some other miner will get a block, and that miner would pack like 1,000 of our transactions and put them in one go, right? And if you look at like block confirmations times, things kind of seemed normal otherwise, right? So the system was working, but there was one party that was basically not accepting transactions, and resulting in this graph, which might even look normal to an outside observer, because they're like, yeah, the transaction volume seems to be low. But no, we were trying to send transactions at this rate, and we're simply unable to. So we tried a bunch of things, like we thought maybe some problem at our end. We were working with our software. And in the end, it basically turns out that for a miner, it was, our theory is that it was actually, they had more of an incentive to publish a block faster than waiting to actually package transactions and then publishing that block, right? So that miner was only interested in publishing a lot of blocks very, very fast, which, as it turns out, how many people are familiar with Gun's work on selfish mining? So this is a work out of Cornell where they came up with a new type of attack on Bitcoin, where a miner would basically publish a lot of, they would find a block but not publish it, right? And then find the next block, and then find the next block, and then publish all of them in one go. So we can't confirm if this was actually happening, but all of the signs of selfish mining were there, and that were probably because of the result of a single miner having just too much compute power, and they were able to like find blocks in quick succession, and they didn't care about transactions at all.
I thought in this case, didn't the Namecoin devs know about this and look into it too? I thought they had talked to this miner, and it turns out the miner just couldn't configure, like they couldn't get it to work.
That might be.
That.
I'm actually not aware
really
of
dumb.
this.
Yeah.
So it could be, completely could be. Like I classify that as, I think I need to move a little bit faster from Namecoin because we haven't talked about our system. But some of the lessons were, so storage limitations is they were putting data directly in the blockchain, right? So there's a limit, the 520 bytes per value pair. This was the biggest problem. If you want to introduce new features, if you want to change the cost algorithm or anything, you basically have to do a hard fork on the network. And you can't do hard forks all the time. And this is why Namecoin started originally, because you couldn't introduce new features on Bitcoin, right? So this is a very important point. I've already discussed failure of merge mining. I've discussed the security. That was the biggest problem. And this is what you're talking about, other unexpected engineering challenges, right? Like so for example, one problem that I am aware of is that Namecoin did a big release of a new version, and then miners just went offline and never came back online. Because to them, it was like the amount of engineering time that this will take to upgrade to the new software is not worth their time. So they basically just dropped out, never came back online. So I think there's something very interesting going on in terms of so it's an ecosystem, what incentives do different parties have, and how do you try to make things incentive compatible that the miner would have natural incentive to participate in the ecosystem. So I'd like to point out that when trying to design a system on the Bitcoin blockchain, some of the problems that Namecoin had were also in Bitcoin as well. You still have the problem of storage limitation if you're trying to put data in the blockchain. And you still have this fundamental problem that how do I introduce new features in the blockchain without requiring a hard fork and without requiring everyone to upgrade their software. And some of the problems of general blockchains are also there. Writes are slow. You have the endless ledger problem, which means that because the blockchain keeps growing, I think Bitcoin's blockchain has crossed like 40 gigs or something. When a new node comes online, it has to process the blocks from the beginning. So there's a long time before a node can actually bootstrap. So the network that we design, if this is the Bitcoin network, these purple, and I think our designer is going to like the fact that my shirt matches with the brand. This purple nodes are actually the Blockstack servers, right? And they don't need to talk to each other. A Blockstack server only talks to a Bitcoin node. Basically what it does is that this is the layer 1, the Bitcoin blockchain. We create a logically separate layer on top that we are calling the virtual blockchain. You're processing all the transactions that are coming in the blockchain, but basically are filtering them out, right? You're like, my protocol does not care about all these transactions. We only care when a name register comes in or when a name update comes in. And we are embedding those operations in the Bitcoin blockchain, right? So the Bitcoin, if you're a Bitcoin node, you will see the raw transaction, but you might not be able to make sense of it. Like what's going on? Why are these people issuing these weird transactions that are not supported by our protocol? But these transactions make sense at the virtual blockchain layer. Right? And we use this design to construct basically a DNS system, right? That you have a name that you registered and you can have a data record associated with it, but we don't keep the data in the blockchain itself, right? So that introduces layer 3, that is routing. You can think of this as your DNS zone file, right? So when you're trying to go to cnn.com, first you get the DNS record that tells you the IP address, which tells you where to get that data. So that's layer 4, the data layer. So the hash of this information is in the blockchain. So it doesn't matter from where you're getting the data record because you can hash it and check that is this the right data or not. So that completely decouples where you get the data from the authenticity of that data, right? Like I could just fetch that data literally from anywhere. I can hash it and then check that this is the right data record that I was trying to get, right? And what that does, so the Blockside server basically handles all these layers. And what this does is it kind of like decouples the design between a control plane and a data plane, right? The control plane deals with the blockchain and is basically responsible for making sure that the bindings between unique names and data hashes is actually secure. And people can update them by signing new transactions and so on and so forth.
What's the DHT node in your system?
So that's the first implementation that we have for the routing layer. But you don't need a DHT there. Like it could literally be any data store. So basically we went for a DHT because of decentralization properties. Every Blockstack server is also a DHT node. So people can just like quickly write data but I would like to say as soon as you open the can of DHTs, like there are all sorts of reliability issues. We are completely aware of them. The only thing is that the data can come from anywhere. For example, we run archival servers that are basically mirroring all the information ever broadcast. His disk is really cheap, so you can actually get the data from there, or even like use that to repopulate the DHT if you need to. But we can take this offline. So the interesting property over here is that now we have actually already written drivers for things like Dropbox or S3 or Google Drive, where you can just like plug in a cloud storage system, right? And you don't have to trust the cloud provider because the data that you're storing is signed by a cryptographic key pair, right? So all of the security comes from the control plane, but you can just treat these cloud providers as dumb data drives where you're just storing the data, and you're completely not associating the security of that data with the provider itself. So this is our graph of like registrations ever since we moved to Bitcoin. I think we've seen some spikes. We got famous in France for some reason. There was an article, this is the aggregate graph. Like this is 33,000 when we moved from Namecoin, and this is how the system has been going ever since. And now we kind of like we have built the entire stack, right? Like straight from the blockchain level to how the data is stored, and we feel much better that we have more control over the design of the system. And an interesting fact is, so this is you can go to opreturn.org. So we are not the only people who are realizing that you can build these new protocols or distributed systems using the public Bitcoin blockchain. Other people are as well. And currently, we are the largest non-financial production system on Bitcoin. Actually, I think we are roughly like 50% or more of the entire usage right now. So that's to scale to this level, we literally broke every single API provider that we were trying to use. We rewrote like every software component that was available. So it took a while, and a lot of hard work went behind this. So I think I might be running out of time. Arvind, how's this going? Okay, I'll try to go over the slides a little bit faster. So remember the endless ledger problem where a new node boots up and they literally have to process the blocks from the beginning of time, right? So we have a solution for this, and Jude is sitting here who mostly designed this. Basically what happens is that we create this consensus hash that you can think of as like a kind of like a heartbeat. It's announced with every transaction. And you use this consensus hash to figure out if you are on the right. Let's say if there is a partition, you use the consensus hash to figure out if you're on the right partition or not, right? So it's like literally like think of it this way, that you're calling up your friends and asking, hey, what's the consensus hash that you see? And they're like, this is what I see. And like, okay, I also see this. Then you call up some other friend, right? And as long as everyone that you care about is on the partition, that is the correct partition for you, right? So that means you are on the correct internet. You're not on a malicious internet where someone is trying to do something sneaky, right? So, and how we calculate this consensus hash is that we also include the blocks like from a geometric series before when actually calculating it, right? So think of this way that a block comes in. There were some name operations in that block that we cared about, so they make their way to the virtual chain. We use that to hash it and get a hash of the Merkle root. But we also look at the blocks previously in history in a geometric series. So like think of this on a log scale, we go back in time, right? And we include that as well in the consensus hash. And the reason why we do that is that now you can get an untrusted database along with consensus hash, and you can actually very quickly just hop through time and realize that this database that I got from an untrusted source gives me the correct consensus hash, right? So that's a solution to fast bootstrapping, that now instead of me processing the blockchain straight from the beginning, I can just download a database, ask a friend, hey, what's the consensus hash that I should expect, jumps through these operations, and get the consensus hash, see if it matches. If it matches, I'm on the right network, right? You can use the same method to actually query these nodes from a mobile client or a light client that does not have their own blockchain with them. So let's say that you want to verify an operation that was announced here. So this is back in time, like further back in time, right? You are here right now. You know that I trust the consensus hash, so I'm on the right version right now. But because of the geometric series of hashes that were used, you also trust this, 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 and that, right? So you can actually jump straight here because you trust this. And now, again, there's a geometric series, right? So now I also trust this, and with this, I trust this node. So you can it's almost like a Merkle skip list that lets you go back in time and very quickly verify that, yes, that operation is part of the consensus hash that I am on currently. So this lets you have like light nodes that don't have the full version of the blockchain. They just know that this is the consensus hash that I trust right now, and they can actually do queries using that. So going back to the general challenges that you have with blockchains, the first is you can't put too much data there. We've solved that by basically taking the data out and only putting data hashes there and writing drivers for storage providers. The next problem is that how do you introduce new features? This is a fundamental problem, right? Because things change all the time. If you're building distributed systems and you want to do a new release, just for comparison, the Bitcoin core developers have now been fighting for over a year to increase the block size from 1 MB to 2 MB. For over a year now, right? And it's basically one line of code change. This is how hard it is to do consensus breaking changes. With our virtual blockchains, you don't need to care about the underlying blockchain at all. You implement new functionality, and you basically release a new version. And sometimes it can break the consensus hash that I was talking about, and those nodes need to upgrade. But it's a different set of people. It's a different set of nodes. You are completely decoupled from the underlying blockchain, right? For slow writes, what we ended up doing is because now the data is in cloud storage, you don't even need to send out transactions on the blockchain for doing data updates, right? Only the registrations are done on the blockchain, and after that, you already have the key pair mapping. So you're just signing data and putting it on cloud storage, and that makes it really, really, really fast. I already talked about fast bootstrapping for the endless ledger problem. And now let's revisit the goals that we had for a decentralized DNS. For censorship, as we discussed earlier, it has to be a state-level actor now, or a company as big as Intel or somebody else who has, for some reason, strong motivation to come and attack the underlying blockchain. And the interesting thing is that when they do, people will notice, because you will suddenly have a different blockchain that rewrites, let's say, 100 blocks deep and announces a fork that is actually longer than what everyone is used to. So even if there's a state actor that launches an attack, it will likely not go unnoticed unless they're very intelligent about it and they slowly try to take over the network. But then you would know that they have more than 51%. Clearly, we don't have central points of failure or trust. And everyone, by default, gets a cryptographic key pair with which you're owning the names. Right? So it's not like you have an account on GoDaddy and that actually owns a domain, and then you go and make another account on VeriSign and you get a certificate and you link them. Like all of that is gone. It's the same system, cryptographic key pairs throughout. You can sign things with the same key pair and so on. We recently launched a command line interface. So you can actually go to blockstack.org, extremely simple to install, just a pip install Blockstack, and you will have access where you can start doing queries. So I'm looking up like fredwilson.id. So this is the .id namespace. You'll get the data record. You can actually also do registrations straight from your laptop, right? So you have a wallet built in, and you can send yourself like $1 worth of Bitcoin and spend like 25 cents and get yourself a name on this decentralized DNS that only you own. For future work, and a very interesting thing that is happening is, like, imagine that the .id namespace was like the .com, It was the first namespace, and we got like 46,000 people registered on it. But now other people are wanting to start the .orgs and the .nets and the something else. So there are all these decentralized systems projects where either they don't have a naming system, or they have been looking for a solution like this, and we have actually started a lot of these partnerships to start new namespaces. And with namespaces, an interesting thing is that unlike Namecoin, we have actually made the pricing, you can actually express pricing in many different ways. So you can either make the names in your namespace free, or you can have an intelligent function that looks at, let's say, the length of the name or the occurrence of certain characters and change pricing accordingly. But it's actually up to the application developers who are starting these namespaces that they actually have a more powerful way to express pricing. I'm actually going to skip that, but the quick point over here is that we did not realize this when we were building the system, but what we actually ended up building is a generic way to specify new types of state machines on top of a blockchain, right? And right now, the state machine that we have built is a domain name system, but there is a library written by Jude sitting here called Virtual Chain, and you can actually go and start writing other types of state machines, right? And that's something very powerful. I wouldn't have the time to discuss it in detail here. What's happening, what's in the pipeline? You brought up DHTs. There are some very interesting ways in which we can actually secure the DHT using this system. I wouldn't go into the details. We are working on having an unbound integration so that these zone files are actually very compatible with DNS, so people can actually start using their deployments of unbound to support the new decentralized DNS system. Jude is working on this very interesting project where he's using this to bootstrap trust between different virtual machines that are booting up in a cloud environment. So this is a project by Larry Peterson, who used to be a professor here, called Open Cloud. And we have done a lot of work on just the identity and authentication services. So there, if you're an app developer, you want to start using this instead of like Facebook auth, you can do that. I didn't get to discuss it at all in this talk. And finally, this actually enables a shift in computing infrastructure where instead of servers being stateful, that they have a lot of state on the users, most of the computing actually happens client-side, right? And when you're logging into a server, you basically sign a request. You can log in. There's no user account, no authentication at the server side. And you can also kind of bring your data with you. So one thing that we are doing is we are writing very simple applications that use this new stateless model. One is an email application that we actually wrote earlier than this system was fully designed. We'll port it over to this. And then you can imagine a simple blogging site that has no user accounts, nothing. You just go in, you sign a request, they pull your information from the .id namespace, you sign the post that you wrote with the key that is associated with it, and post it. And there is a guarantee that this blog post was actually written by this person, no matter where you are in the world. Like you could be in Iraq or Afghanistan or somewhere, and you want to make sure that this data or post was actually written by this person. You just sign it with your key, you post it on the server. As I said earlier, that this project is too big to be the work of any single person. I'm just one person working on the project. Ryan, my co-founder, has done a lot of work on this. Jude is sitting here. And then the academic paper that is currently under peer review is actually co-authored with Mike Friedman. And JP has been helping our company ever since we started doing fundraising and things like that. And then Andrea is sitting here, and she actually was very understanding when I started dabbling with blockchains back in 2013. And she was like, you can go ahead if you're interested in this area, just go and knock yourself out. So we have a bunch of open source contributors and over 600 community members on our public Slack. I would encourage everyone to check out our website, see all the public code, because this is real. This is a production system. It's not just an academic paper, although you can go and read the paper as well. We had our first summit at NYU in September. We capped it at 120, and we sold out. So 120 engineers came and basically talked about what this new system enables, how they're interested in using it. And so we are very excited about the next summit that we'll host this year. So here are the links. All the code is open source on GitHub. And you can go and install the CLI or read the paper or go through our tutorials. And we can take more questions now.